All right, I just want to skim over some aspects of galaxies. This is sort of just introductory material and learning about the parts of galaxies and things like that. But I just want to make sure that as you look through some of these resources in the book, because there's way more in the book than we're going to get to, that we at least all know the highlights to hit. Um, so we'll have the same foundation moving forward. All right, so here is the Milky Way. This is the galaxy that we are embedded in. It's a collection of about 200 billion stars, and of which our sun is just one. Our galaxy happens to be a spiral type. Next time we'll talk about the different types, but um, this is one a pretty common type of galaxy, obviously called a spiral because it looks like a spiral. There are spiral arms. There can be some galaxies have two spiral arms, some have four or more. Sometimes they're more or less tightly bound. If you look in the book or other resources, you might see that there's different types of spirals. There's like type A, B, C. We're not going to deal with that. It's just spiral. We don't have. There's no value in us looking even further at the subdivision of spiral. Anyway, our galaxy is a spiral type. We are not at the center. This is not obvious. I mean, if you think about it, a galaxy is a lot like a forest, and we're sort of plunked down in the forest somewhere, and it's not obvious what the shape of the forest is if you're just in the middle of it, right? Because everywhere you see is a tree. It all looks the same, one direction to another. But we'll talk about how we know, how we finally figured out where we are in the galaxy, what our position in the forest is. And it had to do with measuring distances to globular clusters. But anyway, let's just take it as a given that we know where we are. We are here. We are about maybe halfway out along the disk of the spiral, kind of nestled into one of the spiral arms. Spiral galaxies, the way that they look is from the top, you can see that pinwheel or spiral shape, but they're sort of like pancakes, so that if you look at them edge on, if you look at them from the side, they look pretty thin. It's just a disc. It's called the spiral disc. And then in the middle, there's a nucleus that's roughly spherical shape. That's the main structure of a spiral galaxy, disc with sort of a lump in the middle. If you go to a dark site, this is not clear to a lot of people these days. It was to people in the old days. But if you go to a site without any city lights and you look up, you can actually see it. You can see the enormous galaxy that we're embedded in, which is a cool thing. But it has to be pretty dark because the Milky Way itself is fairly dim. It's a gigantic object and lots of clouds of dust and gas in the way. But if you go to a really dark site, you have to go about an hour outside of the city, any direction. It's a nice cloudless night. You look up and you'll be aware of this. You'll be aware of this band that looks like a cloud stretching all the way across the sky. But it's not earthly cloud. It is the galactic cloud. It's the edge on. It's the galaxy that we're embedded in, because we're sitting here on Earth and we're looking in this particular direction along the disk. And so what we see is this sort of big mess. If you try to look towards the galactic center, right there, you just see a mess. It's kind of obscured by clouds of gas and dust. Spiral. But that's goes. But it's just neat that we can see and perceive, especially once you know what a galaxy is. It's really cool to look up and be able to see the gigantic thing that. One other thing, I don't think the book makes this point as much. I'd like to make this point, but look, here in the spiral arms, there's kind of a clue as to what's going on, because in just about every picture of a spiral galaxy that we're going to see, or if you just Google, for heaven's sake, Google spiral galaxy, you'll get 1,000 pictures. And in just about every picture of a spiral galaxy, you'll see that the disk is tinted blue. And the nucleus is tinted yellow. And that's a clue as to what's going on. Remember, these are giant collections of stars. Why might the disk appear blue. Well, what is the source of blue light? It would have to come from type O and B stars. Those are the only stars that glow with a bluish tint. But if you see O and B stars, if you see the glow from O and B stars, then you also know something else, which is, this is kind of based on what we talked about in the lab assignment for the week. That also means that active star formation is going on basically right now, right? Because O and B stars, what you know about them, they don't live. So if you see their glow, that means they must have formed really recently. And in fact, sometimes in some of the pictures, like the picture I posted on the weekly Moodle page, you see in some galaxies really obviously see these little pink areas, little pink dots. Those are really active regions of massive star formation, because what's happening is those really young O and B stars are lighting up the entire nebula. They're making the whole thing glow. It's mostly and if you remember back to when we did hydrogen glows pink, then you can separate out H alpha, H. But altogether, the spectral tube pink. It's exactly the same color as we see here, just on way, way large scale. These are many, many parsecs. But these are active sites of star formation where it's so hot. The O and B stars that have just been born are so hot that they make the entire nebula glow. All the hydrogen nebula glow. Anyway, in the disk of spiral galaxies, you get this overall blue tint. That's because of the O and B star. And it's no coincidence that also in the disk you see these lanes of dust and gas. Any spiral galaxy you're going to look at, you're going to see in the spiral arm dust. And it's no coincidence, because we kind of know by now that that's how stars are born. They're born out of great clouds of gas and dust. So wherever you find these clouds, you're going to find associated star. Okay, so that's why the disks of spirals are blue. Anytime we see a blue tint in a galaxy, that means active star formation. Young, hot stars are dominating light. And just a word about that, related to the lab we're doing this week. You might wonder about that, because O and B stars, there aren't many of them. It's hard for them to be born in the first place. With every, what do you find in the lab? Out of every 10,000 stars like the sun, you only get maybe 2 O and B stars. Something. So anyway, they're very rare to be born in the first place, and then they die. So how is it that they're light dominant? Well, if you look back in the star parameters chapter or whatever that was, what we said was, if you look back at the table, one O star can dominate the light. They can have luminosities as high as 1 million suns. So even though only 2 out of 10,000 stars might be born as O's, their light dominates, because each one of them can outshine 1 million other stars. So whenever one of them is born, its light will dominate all other stars. So that's why spiral arms tend to be blue, is because the light O's and B's, even though there aren't many of them, their light dominates. They're so much brighter. Okay, what's going on in the nucleus? Because there in the nucleus, it's yellow. Well, if it's yellow, that means that there isn't as much active star formation going on. Whatever O and B stars have been born typically die. They can contribute much of the light. So a yellowish tint means, in a galaxy, it means that that's a population of older stars, right? G's, K's, so on. The O's and B's have died out. So usually those are not regions of active stars. It's kind of it. Okay, so just letting you know that when you look at lots of pictures of spirals, they'll all have the same pattern. Spiral arms are blue, active star formation happening, and then the nuclei of the galaxy is going to be yellow. So for some reason, in the nucleus of the galaxy, not a star. Okay, next. What is at the center? For a long time, we thought that probably what was at the center was a giant black hole. That what happens over billions of years is that black holes that are generated early on by supernovae, the population of stars is really tightly packed. So these black holes spiral into each other and start growing. Because two black holes that collide or coalesce together just form a bigger black hole. And so we thought there's probably a supermassive black hole sitting there at the center of the galaxy. But it was very hard to find because it's not active. Because they don't emit light, there's no active accretion disk. So since they don't emit light, it's hard to. But what we can observe, especially in recent years, there's a video, by the way, you should watch it. It's only like 5 minutes, talking about the discovery of the mass of the black hole at the center. And what they did is they devised a way to look in the infrared band to pierce all the clouds, and they were able to look at the orbits of the innermost stars, S2, some of the innermost stars in the galaxy. They're orbiting this thing. It doesn't just point. And when you look at the video, there's a point. It's like halfway into the video. And what you'll see is you'll see the orbits of these things. What they did is they took a picture every 6 months. And over the course of 6 months, the stars would move a little bit. And so when you stitch all of these things together, you get a location. And so we can watch these things go through a full orbit around the center of the Milky Way, a whole bunch of them. And remember, what is it we need to calculate the mass of the thing at the center? What we need is the separation and the period. Those we can observe. We can observe a full period for these things. And then by knowing how far away the center is, we can figure out the separation. So anyway, what I'm saying is that it's a pretty easy calculation to figure out what the mass is of the thing that's at the very center. And what we figured out was it's a mass of about 4 million suns. And it's tightly packed into an area which could only be. So this was conclusive evidence. There is a supermassive black hole, about 4 million suns of mass, center of our galaxy. It turns out, though, then we figured, well, maybe there's one center of every galaxy. There are lots of so we're not special in that regard. It still is really interesting. At the center of every galaxy, sort of gargantuan black hole with stars around it. Is it dangerous to us? No, because the entire mass of the galaxy is 100 billion, 200 billion solar masses, and so 4 million solar masses. It would be if we got to the center, but we're far enough out, so it doesn't make a difference. But neat. That's a really cool thing that's happening at the center. Around the outside of the galaxy, there's something called the halo that I'll show in the. But the halo is dominated by these clusters. There's about 150 of these things called globular clusters. Globular, the root word of that is supposed to be globe. And they're just spherical arrangements of up to 1 million stars. And all the pictures of them look the same. Here's a globular cluster. And once you've seen one, you've pretty much seen them all. They're different from each other. But what's interesting is by now we've gotten good enough so that we can take HR diagram. We can take the spectrum of stars that are in the cluster. We can make an HR diagram of all the different stars. And remember what happened. The HR diagram, now down here, this is something we hadn't talked about yet, but this is roughly like O, B, A, M, different. Sometimes we measure something called a color index, which is like how much blue minus red star is. But that you can kind of convince yourself that's the same thing. So anyway, all of these clusters have a certain turnoff right there. So only stars up to about G or F are still actually in the cluster. Everything more massive than that has already died, right? There's so many red giants in the cluster because all the more massive stars have already evolved. And so the way it goes, remember, is that you can just read off based on the most massive star that's still on the main sequence. You just read off the spectral type, and then you can calculate the age of the cluster, which is kind of cool. But what's neat is, for all of these objects, for all 150 globular clusters, they're all showing the same age. Really telling us something, right? They're all ancient. They're all about 10 to 12 billion years old. So that tells us roughly how old the galaxy is. Here's where they are. So here's our galaxy, right? Here's the nucleus of the galaxy. Here's the galaxy sort of edge on. There's the nucleus. There's our sun halfway out along the disk. So if we look at it edge on, what we have is this area around the galaxy, sort of football shaped. That's called the halo. And the globular clusters are those red dots inside the halo. Like I said, there's about 150 or so. And once we figured out how to calculate the distance to the globular clusters, then it became obvious that we weren't at the center of the galaxy. Because if all the globular clusters are orbiting the center of the galaxy, if we're at the center, there should be as many in one direction as another. We find that that's the case. When we look at these, they are predominantly one side of the sky. So figuring out all those distances tells us pretty much where we are in the center of the galaxy. Our galaxy is not alone having these globular clusters. This also is pretty common spiral. If you click on this, then the galaxy that's in the first image, the Sombrero galaxy, it has a whole bunch, hundreds of globular clusters around it too. So this is a really common thing, apparently, in the formation of spiral galaxies. That first, a long time ago, you make the globular cluster, and the matter settles down, and starts spinning around, sort of like a pizza dough starts spinning. But these were some of the original first objects made. The globular cluster stayed there on the inside, and so these are sort of like the fossils. This tells us what the galaxy was like 10 to 12 billion years ago. It's pretty common, apparently. All the galaxies went through this evolutionary stage of forming. All right, so this is just an overview into the parts of our galaxy, and then next time I'll talk about different galaxies, because there are different galaxies, hundreds of billions of galaxies we know of now, but they fall into one of three basic. So we'll talk about